So thank you very much. Thanks to the organizers for inviting me to participate in this great workshop. I really enjoyed the talks. I'd like to tell you about work on minimal surfaces in random environment. In this talk, I will discuss two works, one with Barbara Dembin, Dor Elboim, and Daniel Hadas, and one with Michal Bassan and Shoni Gilboa. Dor Elboim is here in this conference too. Okay, so, and I'm at Tel Aviv University, but moving next year to the University of Maryland, so a bit closer to here. What are minimal surfaces in random environment? We will discuss that very soon, but here you see a few pictures, and I'd like to give you some features of these pictures. Here you see a path. This is actually a first passage percolation path, if you remember from yesterday. But what I'd like you to notice is that the path is a one-dimensional surface. Path is one dimension, and by the letter little d, I will denote the dimension of the surface. So this is one dimension, and this path is in a two-dimensional space. So by the letter n, I denote the codimension. So it is embedded in one dimension higher, so the codimension is 1. Here, a similar path is embedded in 3 dimensions, so its codimension is 2. Okay? So there are these numbers that will recur throughout the talk, that d is the dimension, n is the codimension, and we will also introduce capital D, which is d plus n, is the overall dimension, the ambient dimension. Okay, so, and here you see a two-dimensional surface in three-dimensional space, so little d is 2 and little n is 1. And what makes the minimal, what makes this a random environment, this is in the next few slides. So let me give an example. Example meaning a model we would like to investigate, but we don't really understand how to do so, so it will serve as motivation for other models that we are able to investigate better. So what is the example? It is the model of first passage percolation that was discussed yesterday by Alan Hammond. But let me just remind you, so in this model of first passage percolation, Alan discussed an integrable version, I discussed a general version. You have the ZD lattice. It is Z capital D because that's the ambient dimension. You have the ZD lattice, and to each edge there is associated a number, a positive number, that is the weight of that edge. These numbers will be this tau E over here. And what you want to know the shortest path between two vertices. So given numbers on edges, ZD becomes a metric space where the distance between two vertices is the sum of the numbers on the shortest path, the path with the smallest sum of the numbers that connects the endpoints. And these numbers will be random. We take them to be independent, identically distributed. For instance, uniform on 1, 2. Maybe in this picture is uniform on 0, 2 because there's some, or 0, 3. I don't know. So for instance, uniform on 1, 2. And we wish to study in this random environment the minimal paths, the geodesics. Geodesics is the same as minimal paths. Notice that this is a one-dimensional minimal surface because it minimizes the distance. So it's a minimal surface in a capital D dimensional space, and we would like to understand the large-scale properties of this random metric space. For instance, the geometry and lengths of long geodesics. Let me indicate that by a picture over here. Suppose we're in 2 dimensions, and we want to understand the geodesic between 0, 0 and L0. How does this geodesic look like? Well, it could look in many ways. Maybe it starts going like that, then goes a little bit backward, then up, like this, and eventually reaches its target. Maybe this is the geodesic. What features do we want to understand about it? We want to understand its length, meaning the sum of the numbers along the path. Later in the talk, this will be called the energy. The energy of the path, the same as the length. And we would like to understand the geometric fluctuations. You may expect, it is natural to expect that the geodesic is close to a straight line, because in the before we added the weight, the geodesic was the straight line. Maybe the weights don't add that much. So if we put here the straight line, we can measure the distance from the straight line. For instance, this distance over here, maybe in the midpoint. And it is expected in 2 dimensions that this distance over here, denoted L to the xi usually, that this L to the xi is really L to the 2/3 for d equal to 2. In 1 + 1 dimensions, as we say. It is expected, but let me tell you that it is open, even that it is close to a straight line. That is, in what is the weakest sense you may expect it to be close to a straight line, the weakest sense is that, this L to the xi is little o of L. So we do not even know that it is not a macroscopic triangle. Notice that if it was a macroscopic triangle, then it would have L excess edges. L excess edges compared to or order L excess edges, and each edge costs you at least 1 if these are the weights. So you're paying way more, and somehow this is the minimal surface, and we do not know how to rule that out. So the situation is pretty bad, although there are some results on these models, even by myself and co-authors, but many others way before.
It depends strongly on your choice of bounds on the distribution. I mean, if it's uniform from 10 to 11, then you'd be much closer.
Yes, you're correct. It depends, and it is clear also that if the weights are between 1 and 2, then it cannot be that you have 1 million L excess edges, because you're going to pay 1 million L times 1 for each one, and whereas if you just took a straight line, you'd pay at most 2 times the length of the straight line. So you're right that the distribution makes a difference, but little o of L is open for all of them. There's not a single weight distribution, well, let's say a compact support bounded away from 0, for which we know it's little o of L. So whichever you prefer. Okay, so you can do this in 2 dimensions as in the picture, or you can do it in 3 dimensions. You can imagine, looks the same. But the fluctuation exponent, so this kind of distance is unknown in any, not proven in any dimension. And in 3 and higher dimensions, it's not even quite conjectured. It's not even clear what it should be. I'll get back to that. Okay, so this was an example of a 1-dimensional minimal surface in a d-dimensional space, and there was a random environment, which was these numbers. Now, let's try to do a surface. How would you define a random minimal surface in a random environment? So instead of a line, a surface. Here is a possibility. Example 2. Again, we will discuss this, but only briefly, and much of the talk will be devoted to another model that is easier to analyze. So here's a way you can do it, kind of statistical physics-minded, or you may think of it in combinatorial terms. I will explain. So let us consider an Ising model, but in this Ising model, the energy of a bond, the energy, if sigma u differs from sigma v for some edge, then you don't pay 1 in your energy, you pay some cost that is associated to that edge. So in fact, it is the same setup as before. Each edge of ZD has a number associated to it, and this number is the cost that you're paying if that edge is not in agreement. And then what do we do with this Ising model, with this random bond Ising model or this ordered Ising ferromagnet? We take these numbers random, as before, uniform on 1, 2 IAD. And we may do the following. We may place the model in a box with Dobrushin boundary conditions. So maybe I draw this here. I take a box, and I put Dobrushin boundary condition, meaning that on the upper half of the boundary of the box, I fix the spins to be plus, and on the lower half of the boundary of the box, I fix the spins to be minus. And then I ask for the configurations of pluses and minuses in the box that minimizes this energy. So it is, in fact, I'm trying to find a way to put an interface between pluses and minuses such that the cost of the interface is as minimal as possible. So it is like a surface that interpolates the boundary conditions that has the minimal sum of weights along the surface. It is precisely a surface because an edge is dual to a plaquette, and if for every edge in the interface you take the dual plaquette, these actually form in this picture, 2-dimensional surface, like in the plaquette percolation discussed by Paul Duncan and Ben Swinehart earlier in this conference. We have a way to generate a minimal surface in a random environment. And in this picture, the dimension is 2 and the codimension in 1 is 1. In general, if you do this in Z capital D dimensions, then you have codimension 1 surfaces. Little d is capital D minus 1, as indicated here. Okay, and if you are more combinatorially minded, this is exactly the same as thinking of ZD with these weights as a network and finding the minimal cut which separates the upper half of the boundary from the lower half. It's exactly the same thing. So if you come from that, in particular, there are good algorithms. If you come from that world, maybe that speaks to you most. If you do it in 2 dimensions, you coincide with the previous model of first passage percolation. And later in the talk, I will speak about recent work on this model with Michal Bessan and Gilboa. But for now, I move on. So we had 2 examples. One of the examples had d equal 1 and general codimension. And the other example had n equal 1, codimension 1, and general d. Okay? So we had 2 examples. Now I will speak about another model. As I write here, it is a model that we feel is more amenable to analysis, so we're able to do more with it. And actually, I'm advertising the model. I'm feeling that this is, by just knowing the model, you're opening a venue of research because you can try and investigate. It's easier to investigate this, it appears, than others, and not much investigation has been done. So I'm advertising the model. It is a model of d-dimensional surfaces in a capital D, which is d plus n, dimensional space, a minimal surface in a random environment of general dimension and codimension. This model has been discussed a lot in the physics literature, but it has hardly received any investigation in the math literature. So it has literature in physics going back 40 years, but in math, very little. Here's the model. It's not that complicated, but it takes a little while to get used to. So there are several objects needed to define the model. One object is the surface itself. The surface itself is going to be a function from the ZD lattice to Rn. So let me illustrate that in 1 + 1 dimensions over here. So for instance, if d equal n equal 1, then what we have the one-dimensional lattice. This is a copy of Z. And at each vertex of the one-dimensional lattice, we have a copy of R, like so. And then our minimal surface is some path that connects points on these copies of R. Okay, like so. So it is very much like this kind of surface, but it has additional features. For instance, we are not allowing that on any vertical line, there is more than one intersection with the surface. We're forbidding such things, so there are no overhangs, as we say. And we're not taking integer heights, we're taking real heights. But other than that, it's a bit similar. Now suppose you wanted to do it in 3-dimensional space, so you took d equal 1 and n equal 2. The way this is structured is that you have the one-dimensional line, and at every vertex of the one-dimensional line, you have a plane. You have a plane, and your minimal surface, or your surface, is going to choose a point on each of these planes. So it's going to do this and that, and this and that, and so on. And in this way, it is like a 3-dimensional movement, because it chooses a point on a plane at every point. And again, it does not, at each vertex, there's only a unique point. So there's no this going back, so to speak, no overhangs or something like that. That is how we model a d-dimensional surface with codimension n. If we are in d equal 2 and n equal 1, I don't know if you will see it if I write on the bottom here. Will you see? Probably not. So, okay, so I do it here, and I still don't know if you can see it. I could erase something, yes, and then you definitely will not be able to see it. So I take a 2-dimensional box, and at each vertex of the box, I put such a line, and then my function chooses a height on each of these lines, and in this way it forms a surface. So I don't know, it chooses a height. It's very hard to draw, but somehow a surface. I hope you understand. So this is the surface. So I've told you one ingredient. The next ingredient is the environment. The environment will be random, so sometimes I call it the disorder, because when it's random, it's the disorder. So let me put in parentheses disorder. The environment is the following. It is a function eta from ZD times Rn to R. It's nice to have infinity too. So what does that mean? that means that on each of these fibers, on each fiber above a vertex, I have a function. Let me denote the function by purple. So I have a function, a purple function over here, and another purple function over here, and another one, I don't know, maybe looking like this here, and another one there. And on each of these fibers, I have a function. This is my environment. The environment is going to tell me if this location is a good one or a bad one. A low number of the environment is a good position. A high number of the environment is a bad position. If the environment is infinity, it means you cannot pass there. That's a point that is forbidden to you. Okay? So you want to find low numbers on these fibers, and if you do it in high dimensions, then the high codimension, then the function lies on this plane. So it tells you on each point of the plane if you like it or not. And similarly here on every fiber, there is a function of this sort. So this is the environment. I like to add also the environment strength parameter, but it's not so relevant to my talk most of the time. So you may just fix it to be 1 if you don't like it. And that's almost all of the model. Now, when we have these ideas, we have an energy function. And what we're going to do, we're going to minimize the energy function. So that's how we're going to create a minimal surface. So it is the ground state or the zero temperature configuration of a Hamiltonian, of an energy function. And what is the energy? It is actually a rather simple expression. We're going to pay something. This is an elastic energy component. So we're going to pay something if the surface bends. So we were going to want to make the surface flat. Because whenever it bends, whenever phi u is different from phi v for adjacent vertices, you pay an energy. And the energy cost is quadratic in the amount that you change. However, so that one wants to keep you flat. So if you put 0 boundary conditions on the domain, and you just had this component over here, then your minimal surface would be flat completely. But now there is a component that wants to roughen you, and that's the component of the potential energy of the environment. So the surface at the same time wants to minimize the amount that it changes. So here, when you see this surface made a big jump in the beginning. So here there was a big jump over here. So it's going to pay a quadratic cost for this jump. But this quadratic cost may be justifiable because maybe it found a very low value of the purple, of the environment function, and so on. But it does a global optimization. It's not local. Okay, so all in all, the minimal surface is probably not going to be flat. But hopefully it's going to be close to flat. That's actually what we would like to investigate. For a given distribution of the disorder, we would like to understand how rough is this surface. So that's the model that we would like to study. We're going to study it on a domain with a given boundary condition. So actually for all of the talk, the domain is just going to be lambda L, which is minus L. And you can put any boundary condition you like, but most of the talk will have boundary conditions, boundary values, 0. So that just means that phi, our surface, equals 0 of lambda L. That's most of the time, because as it turns out, it doesn't matter for this model in some sense. Okay, this is the model. I hope you understand what it is. I'll write it in a succinct way over here as 1/2 norm of the gradient of phi squared plus lambda eta at the position v at the position phi v. Okay. So this is the model that we would like to study. We call it harmonic minimal surfaces in random environment. Previously, there has been some investigation of it. It was called, as we will see now, the elastic manifold or the Invisit-Burger's equation with kick forcing noise. So you can choose which one you prefer. So here is some literature in this model. So in the mathematics literature, it has mostly received attention when d and n equal 1, under the name of the Invisit-Burger's equation with kick forcing noise. And it appears to be mostly or only in the work of Yuri Bakhtin with co-authors. Several works exist from 16 to 19, and an earlier work, which is not strictly in this setup because the base is not ZD, it's RD. An earlier work appeared with Kator and Hanin in 14. Now, this is also related to Brownian polymers in random environment, because that would be like a positive temperature version of this. And there is a review of such literature by Comets-Kosko. Again, it is a d=1 literature. So there isn't actually any literature on exactly this for surfaces. There is something. So Ben-Arous, Bourgade, and McKenna just recently considered the model for fixed d and n going to infinity. But the reason I say that they didn't do what we're doing is that the questions were different. It was the same model, but they didn't ask about the geometry of the minimizer. They asked about how many critical points does this Hamiltonian have, what is called landscape complexity following Fyodorov and Ledussal. So in fact, for surfaces, nobody's investigated this. And for d=n=1, there has been investigation. But for d=1 and n larger, very little, maybe only in this Brownian polymers type. So there is Wuttrich, for example, doing Brownian polymer in a Poissonian environment. Okay, and in the physics literature, on the other hand, there has been a lot of attention to this model. It is impossible to list the entire literature here. Actually, I should have listed the Hughes and Henley as well. I don't know why it's not here. But you can see a few papers, and you can see several reviews as well. So it's been so long that there's a lot of reviews of this model too. And the reason is that this model models exactly what we started from, the interfaces of the random bond Ising model, random field Ising model. It's related to random field XY. I will comment on these issues. Okay, so now we would like to investigate this model. And the first thing to do when investigating this model is decide on the environment. Because if I take the environment to be 0, say, then the whole thing is flat. It's nothing to do. So of course, I need to take it somehow non-zero. And I will now describe. Now, motivated by these minimal surfaces described in the beginning, it is natural to think of an environment that is IID, so kind of as independent as possible. Of course, because it takes values on the real line, it can't be exactly IID between every 2 points. So indeed, this is our initial focus on distributions of the disorder which are independent. Here's an example that we study in detail. The example of smoothed white noise. So you may do the following. You may decide that between different fibers, your function is independent. And this we will indeed always do. And then on the fiber, you can't make it IID, but you take a white noise and you smooth it by convolving with the bump function. So some regularization of white noise. Indeed, eta v are independent, and eta v at the height t, at the base position v and the height t, the environment on the fiber at height t, is a white noise associated to the base position, convolved with the bump function to smooth it out. And then there's some requirements that, most important of which is that the bump function has range 1. So it's 0 when you go beyond 1. So bump function is simply something like this. Just that. Okay, so this is a main example. All of our results apply to the main example, but what is interesting is that our results also apply for a much, much wider class of things under certain abstract assumptions. And this is not just for kind of fun and generalization. I feel that there are indeed some interesting phenomena if you go beyond just a simple example like that. There are also other examples I could have given, a Poissonian disorder, but we only for this one do we prove everything, so we don't. I don't list it at the moment for time considerations. So there are some abstract assumptions. Maybe I will not have time to really look at them in all detail, but let me say one has to do with the stationarity of the disorder. Another has to do with a certain independence of the disorder between vertices and at range 1, so you lose correlations very quickly. Another is concentration. You may say that's some kind of cheating because we're looking at the minimal energy, which is one of the objects of study. So we're interested in the minimizer of the energy, which is one of the main objects of study, and we're making assumptions on it. You may say that's cheating, but the assumption we're making is rather mild. It is the kind of concentration you get from Hofding's inequality or Talleyrand's inequality. It is the kind of basic concentration that everyone has at hand for all these examples. Indeed, it is easily verified in this example too. So it is not on scale, so to speak. It's not the true standard deviation. It's just the basic concentration assumption. And these are our assumptions under which we can prove theorems. Let me just mention that if you don't require, say, the concentration assumption, then this really allows you a wide generality of models because you may, for instance, vary even say the disorder strengths between vertices. So make a few vertices have very strong disorder, other weak. So there's a wide variety here. It doesn't have to be kind of stationary in space, only in height, so to speak. Okay, and there is something called periodic disorder. I'll go back to it later, which is contained in stat and cons. Okay, so what do we actually prove about this model? So our main focus, as in this picture over here, is to study the deviation of the surface from a straight line or a straight plane, if it is a surface. We put 0 boundary conditions on this on the boundary of this domain, and we want to know how much it fluctuates. And here are our results. Let me perhaps start with a summary in this table over here, easier to read. So in some sense of localization, and in a different sense of delocalization, under some assumptions for this and other assumptions for this. But anyway, everything holds for smoothed white noise. We have the following. In dimension, when the codimension is 1, it is expected, as we said, that the height fluctuations are L to the 2/3. And we may show that they are between L to the 0.6 and L to the 0.75. In dimension 2, where such a model has not been investigated before in the mathematics literature, there are numerical simulations of Middleton saying that it should be still a power. But by the way, this by itself is something rather perhaps surprising to some of you, because if you look at this Gaussian free field component, you are well aware that it has usually square root log fluctuations in 2 dimensions. However, the disorder is so strong that even at 0 temperature, it roughens it all the way to a power. So also the fact that, in fact, you have power delocalization dimensions 1, 2, and 3, sub-power delocalization dimension 4.
This is n equals 1. This whole term is n equals 1, not n equals 2.
D equal 2, though, it's a surface of codimension 1.
Oh, n is a codimension. I'm sorry.
That's okay. So that's why it's here. So it's a surface of codimension 1, and it, unlike what we are used to from thermal fluctuations, it doesn't go to height which is logarithmic. It goes to a height which is a power, predicted to be this power. Even in dimension 3, it does that. In dimension 4, it is sub-power, but still delocalization. And dimensions 5 and higher, it is localized. That by itself is this general feature was not known mathematically. We actually proved this general feature for any codimension as well. So this table lists the specific numbers we get for codimension 1, but for any codimension, we have the general features that it is power low delocalized in 1, 2, 3, and sub-power low, but still delocalized in dimension 4, and localized in dimensions 5 and higher. In dimension 2, the predicted roughening exponent is 0.41, and we get it between 0.4 and 0.5. In dimension 3, 0.22, we get between 0.2 and 0.25. Here it's predicted to be a power of log L. I should say these are numerical simulations, and this is a functional renormalization group argument. This one we took from Emig and Natterman, and we get between log L and log L to 0.2. So we have these general features and bounds. Let me say a few words about the more precise statements. On a more precise statement, in terms of the upper bound, we get pointwise bounds. So we say that no point fluctuates more than what's listed here. The bounds that we get do not depend on the codimension. Actually, it would be better if they would improve with codimension, but they do not in our analysis. And whereas for the lower bound, we do not show that a specific point fluctuates, but we can show that 1% of the heights reaches the levels listed here. For instance, the level listed here, 1% of all heights. And what we get as a lower bound, this is called the Flory approximation in physics, same Flory from self-avoiding walk arguments, if you are aware. We get the Flory approximation as a rigorous lower bound at all times, but something that, and that gives us L to the 4 minus D over 4 plus N, but something that extends this fact for geodesics. In general codimension, we are also able to show that the fluctuations are at least square root of L in any codimension. This relates to an interesting open problem in physics, still open in physics also, that it is unknown whether the geodesics in some codimension have exactly square root L fluctuations, or whether they always exceed this quantity, even exceed polynomially. It is unknown, but we are at least able to justify that they're always at least square root L. So we still do not resolve the physics problem, but maybe we get the closest, so maybe there is a chance. And these are some references from the physics literature. So these are our results on the localization and delocalization of surfaces. Maybe I should say, just emphasize again, for surfaces there was no work, so everything here is new. But even for geodesics, this bound was not proven earlier in any model of point-to-point non-integrable. Point-to-point geodesics, only for point-to-line by Wuttrich and Bakhtin and Wu. And in higher dimensions, this bound of L to 1/2 was also not proven before, but was proven by Wuttrich if you are at a positive temperature, and also for point-to-line, and by Newman and Pisa, but in a different, so for almost geodesics in some direction, so it wasn't geodesics exactly. Okay, so these results are even new in one dimension. Okay, and then we have a second set of results. This was one set of results on the height fluctuation. A second set of results concerns the so-called scaling relation. What is the scaling relation? So I already introduced one exponent. I said that the fluctuations should happen to a power xi, L to the xi. That's a notation for the amount of fluctuations. There is also a second fluctuation exponent. The second fluctuation exponent concerns the fluctuations of the energy. You take the minimal energy, the energy of the minimal surface, and when you change the disorder, you ask by how much does the energy of the minimal surface change. So what is the fluctuations of the ground energy, or fluctuations of the energy of minimal surfaces? And the physicists, again, usually denote the height fluctuation by L to the xi, and the fluctuations of the ground energy by L to the chi. And perhaps those of you who have worked on first passage percolation have seen before the relationship that chi needs to be 2 xi minus 1. So this is a so-called scaling relation. So there is this scaling relation actually given rigorous proofs in the work of Wuttrich and the work of Chatterjee, but only under unproven assumptions. This is the scaling relation for d equal 1. What is less known is that there is also a scaling relation, and very recently rigorous proofs in 1 + 1 dimensions by Basu and Sly for rotational invariant models, and there it is without unproven assumptions, with assumptions to be verified in a sequel paper. But in any case, what is less known is that there is a scaling relation that is also true for surfaces, where chi is 2 xi plus d minus 2. So indeed, if you're in the geodesic case where d equal 1, then this becomes 2 xi minus 1. But if you have a surface, then whatever d is. This is the scaling relation proposed, for instance, in Hughes and Henley. I don't know if it goes back any further than that. And we're able to give rigorous proofs of this relation for our model. Rigorous proofs of versions of this relation. So when you look at the relation, it talks about a connection between exponents, but we do not know that the exponents exist. And there are many, perhaps, ways to interpret this. Are there any sub-power corrections to this? And what exactly does it mean? So we give rigorous versions of this. Here are the versions that we're able to prove. So this is a version of the direction chi greater or equal to 2 xi plus d minus 2, and it is as follows. You look at the ground energy, the energy of the minimal surface, and ask for its deviation from the median, from its median. The chance that it deviates by h squared L to the d minus 2 is at least the chance that the height fluctuations of the surface are h, are at least h. So if you take some h such that the average height of your surface has a chance to be there, suppose L to the xi, let's write h to be L to the xi. Suppose you have, I don't know, probability 1/2 to be more than L to the xi, then the energy fluctuations have 1/2 times 1/3 chance to be at least L to the 2 psi plus D minus 2, which is what is written here. So that is why this is chi greater than 2 psi. But let me emphasize that this is a much wider, this version of the scaling relation encompasses more than what's written here. First, it is without any corrections, say sub-power corrections. It is exactly a relation between the distributions of these two quantities. Second, it holds also in the tails. So it doesn't necessarily, you don't have to be in the bulk of the distribution. If you look for H extremely large, where this probability is very small, well, this probability is also of a similar order of magnitude, as a lower bound. So it holds also in the tail. Third, it is proved under the stat. I think this one's only under stat, but the other one is within depth. So it's proven for a very wide class of disorders with the same constants. So the scaling relation is really a universal feature that holds, even, for instance, if you take a disorder that is not identically distributed in space, so changes between base vertices, then this relation continues to hold uniformly. So this is one direction. For the other direction, we have a slightly different notions, both of the energy fluctuation and of the height. I should have said that here, if you want, you can replace the average by the pointwise height, but we know how to do that only in dimension 1 and dimension, so geodesics, or in dimension 2, but with a log loss. We don't know how to do it in dimension 3, say. So, okay, but just to mention. In the other direction, we use slightly different notions of ground energy fluctuations and height fluctuations. The height will be measured by the maximum. Instead of taking the average height or the pointwise height, we take the maximum. Compared to pointwise, it's rather compatible. And what this is, but for the energy, let me explain. What is written here for the energy fluctuations? So maybe I will have to erase something. Let me erase this. So I'll just keep the scaling relation on the board here. So what we are doing, we take, let's do a one-dimensional picture first. So in one dimension, this is our domain. We take the middle of the domain, and we take the disorder that lies above the middle of the domain on these lines, the disorder given by these purple functions here, and we resample that disorder. That is, maybe it would have been natural also to resample all of the disorder. We do not do that. We only sample the disorder in the bulk, in the middle half of the domain. And then we take the difference of the minimal energy between the original disorder and the resampled disorder, resampled in the bulk of the domain. And the result is that the probability that this energy fluctuation exceeds h squared L to the D minus 2 is less than the probability that the maximum exceeds h. So again, if you have L to the psi here, such that this is less than a half, then also fluctuations of this order will be less than a half on the left-hand side. So it is chi less than 2 psi plus D minus 2. Again, it holds uniformly in the for any codimension, and it holds also in the tails, and it holds for a wide class of disorder distributions uniformly. Now, regarding the fact that we resample the disorder only in the center, this may be a priori objectionable. You may say, no, it would be more interesting to resample the disorder everywhere. However, we're able to explain that there is a non-trivial contribution to the energy fluctuations from the boundary. And if that is taken into account, then this scaling relation need not exactly hold. So at least if you allow a wide variety of disorders. So we do have, for geodesics, a more refined scaling relation that takes into account the boundary contributions. So here what we're saying is that the energy fluctuations overall, when you resample the disorder everywhere, they're bounded both above and below by the height fluctuations, but you have to take the height fluctuations according to the distance from the boundary. If you take the height fluctuation at distance k from the boundary, then you need to divide it by k. So how to explain? When you read when you read the scaling relation in dimension 1, chi equal 2 psi minus 1, then what this suggests to you is that the standard deviation of the ground energy is like the height fluctuation squared divided by L. And what I'm saying here is that if this height fluctuation is measured at distance k from the boundary, then it should instead be divided by k. And then this is a two-sided bound. That is, if you take the maximum over the numbers you can get here for k, so if I write here height fluctuation at distance k from boundary, okay, there's no room, at distance k from boundary, and I divide it by k, then it provides a two-sided bound if you take the maximum over k or the sum over k. In one direction it's the sum, the other direction it's the maximum, but we expect one term to be dominant anyway, so that those don't differ. In any case, they can differ by at most log in the way it's written. So we know that there is a two-sided bound. It does happen, apparently, that if you take the usual IID disorder, then the main term is the bulk. But in a wider class of disorders, it could be that the boundary contributes, and this then is a two-sided bound. So we feel that this is like the actual scaling relation, and the fact that the bulk term is dominant, that's an extra step beyond it. We also feel, that's an interesting fact, that if you look at surfaces, so if you look in 2 dimensions, then I think in very high codimension, it may be that the boundary term overwhelms the bulk term, even for IID disorder. That is, this relation cannot hold as is if you do not take into account the boundary terms separately, I think, in higher, for 2-dimensional surfaces in high codimension. It is a guess, though. Okay, so with this, I finished the discussion of the scaling relation. In the last few minutes, there are several things I could do. One thing is to tell you about ideas from the proof, and actually, I'm not going to do much of that. Instead, I would like to tell you a few additional interesting facts, but I will tell you one idea from the proof, maybe a very important idea, the so-called main identity. The reason that this model is more amenable to analysis than other models you could write is the following identity. Let me write the energy function, as I've done before, as the norm of the gradient of phi plus the potential energy contribution. And let me consider what will happen to the energy if I shift my surface. I take the surface plus another surface, and at the same time I shift my disorder. And the way this is going to be is that I take my surface and I add something to it, and I'm shifting the disorder so that if the surface used to take this value and it's added, I moved it up, then the disorder value at that point is also shifted up, so that the new disorder value will be the same as the old disorder value. I look at the shifted surface in the shifted disorder, and I take the energy of that compared to the old energy. Then that has a simple formula that does not involve the disorder. It is the inner product of the surface with the Laplacian of the shift and the Dirichlet energy of the shift itself. And this is an equality. So this generalizes, it's very simple also. This generalizes the fact, for instance, that in the Gaussian free field, if you put tilted boundary conditions, you just get the harmonic extension of the boundary conditions plus the original distribution. Then this will show you that this also holds in this model. That's why I said the boundary conditions are not that important. The proof is a one-liner that I will not go through. And as it turns out, this main identity used sometimes for harmonic functions, where the Laplacian is 0, and sometimes for non-harmonic functions. That's very important, where this term is non-zero. This is the driving force for all of our results. Somehow, this one identity is the important tool for all of the results. Instead of delving into some ways to show you such results, for instance, some simple versions of localization, I can show in 2 slides, this slide and the next slide. But instead of going over those slides with you, and then another simple version of delocalization also takes 2 slides, but in a very small font. So you probably don't want to see that anyway. But small font, and for some reason it takes forever to list those. I should do something about that. So instead of going with you over these I just want to impress upon you that in 2 slides you may actually list a simple version of localization and a simple version of delocalization, meaning that it's not so long if you just want simple versions. And I would like to tell you something about other models very briefly and finish. One thing is the model that we started with. If you remember, we started with the model on ZD of surfaces, the minimal cut or the interfaces of the disordered Ising model or random bond Ising. What about that one? You may ask, we made a certain approximation by passing to this model. Is this approximation to be justified? I mean, do we expect that the behavior of this model is the same as the behavior of that model? So there is an interesting thing here. Maybe generally we do, but not always. That's an interesting fact. So we proved with Michal Bassan and Shoni Gilboa, and there was a previous analysis by Bovle and Kuski in so-called solid-on-solid approximation, but we did it with overhangs, which turned out to be much harder. We proved that if you have, recall that there is a disordered distribution on edges, the coefficient of the Ising, that's a random number on the edges. If that disordered distribution is concentrated, so for instance, if it's uniform AB and B minus A over A is small, if it's very concentrated, then the surface localizes already for a 3-dimensional surface. So you need to recall that table from a few slides before, which said that there is delocalization up to dimension 4. And here we have localization in dimension 3. So there is a difference in behavior between this surface and the other one. However, we think that this difference in behavior is only due to the fact that this surface can take integer values. And so the real values is what allowed it to fluctuate earlier. So we conjecture that in fact in dimension 3, there is a roughening transition, the disorder strength. If it's not so concentrated, there will be delocalization to power low height. Dimension 4 is a marginal case. Maybe it doesn't have this transition. But dimension 5 and higher should localize always. So we have these conjectures. In dimension 2, we also have a delocalization conjecture. That should be more accessible. We hope to work on that. OK, so this was just to go back to the previous model and connect the two. In the last few minutes, I mentioned that although we've studied here a disorder distribution eta, which is an approximation of IID, there are other choices that would make sense. For instance, if you go back to this Ising model in a box with the Brushin boundary condition, we studied the random bond Ising, where the coupling constants are random. There is also something called the random field Ising model. How would the interfaces for that look like? This is again approximated by this model, but now you should take eta to be Brownian motions. And indeed, in the physics literature, this received a lot of attention. So this is called the random field disorder. And that one is actually, in some sense, easier to analyze. In a sequel work in preparation with Barbara Dembin and Dor Elboim, we're able to analyze this even for not just Brownian motion, but fractional Brownian motion with this Hurst parameter h, and prove that the height fluctuations take exactly this form. So this time we know the fluctuation exponent. For instance, in 1 + 1 dimension for Brownian motion, the height fluctuation should be linear. So they should actually form macroscopic triangles. You can kind of see here that they fluctuate more. And this is irrespective of the codimension. It doesn't change in higher codimension. So this is in a sequel work. There is interest also in periodic disorder. This relates to the random field XY. Our localization results still apply, but I don't think I have time to do that, to say that in any other detail. A linear disorder is kind of a toy model because it's exactly solvable with real values, but this conjecture of a roughening transition might be easiest in that case. Even for linear disorder, we don't know how to solve it. This conjecture. But again, I don't have the time to go into that. So let me finish the talk with several open questions. So these are just selected, but there's really a lot of open questions in this field. One can try to improve the exponents. For instance, to address the physics open problem, that geodesics in 3-dimensional space or 4-dimensional space, or some higher codimension, whether or not they have fluctuations exactly square root L or larger. That would be very interesting. It's not known even in physics. Periodic disorder has a lot of interesting conjectures. There's super roughening in 2 dimensions. and apparently log fluctuations in 4 dimensions. So this is not listed here, but there is a reference. The roughening transition that was mentioned in the disorder strength. Interesting thing that was recently proven by Reedy, Basu, and Alan Sly for a different model is to understand the concentration of ground energy on the scale of its standard deviation. So in 1+1 dimensions, Reedy and Alan found a technique to do that. Can that be done in other dimensions too? So there is a lot of, these are basic issues. Thank you very much.